so with multiplication, let's just start with decimal. So let's say we're multiplying two two-digit numbers. So I don't know, 15 times 23, something. How do you do this? So what you do is you look at this digit here and you multiply this by the top number. So 3 times 15 is going to be 45, and we'll just write that down here. Then we look at the next digit. This is 2. 2 times 15 is 30, but here we're going to shift it over, right? Because it's the next bit. And you might put an X here or a 0 here. And you would shift this all over, and then you add the results to these results together. So 5 plus 0 is 5, 4 plus 0 is 4, 3 plus nothing is 3. So this result here would be 345. The multiplication works the same exact way in binary. You just have to be a little bit careful. So let's say we take two 4-bit numbers. And for this, we're just going to worry about positive numbers. You don't have to worry about negative numbers. So here it's the same exact process. We're going to look at this bit here. So 0 times this number, well, that's just going to be 0. Then 1 times this number, but we're again going to shift it over because it's the next digit. Because really, this is not 1 times this. This is 2. Right? That's the binary number 2. Whenever you see a 1 in this place, that means 2. So 2 times this is going to be 1, 0, 1, 1, but shift it over. And then we have 1 times this. Well, that's going to be just this number again, but shift it over 2 bits. And then finally, we have 0 times this, which is going to be 0, but shift it over 3 bits. And then we add all of these together. So that's just going to be 0. That's going to be 1, 0, carry a 1, 0, carry a 1, 0, carry a 1, 0, carry a 1, 1. So this would be a result. Well, the problem is, you know, as we've learned with architectures, architectures are a fixed number of bits. So like, let's say our computer is a 4-bit computer. Well, that's a 4-bit value, and this is a 4-bit value, and our result is 7 bits. That's a problem, right? Because we can't store this in a register. If our starting values are 4 and 4, we can't store this result. You could say, oh, we'll only multiply together 2-bit numbers, but that sort of is defeating the purpose at least slightly. In a lot of cases, you know, if you're dealing with 32-bit numbers, you know, multiplying two 16-bit numbers might be okay, and that might be more than enough for what you need. But really, you'd like to be able to multiply larger numbers together. So how do you do that? Well, what we'll do is, instead of storing or trying to store this result in a single register, we'll store it in 2 registers. We'll store a high register and a low register. And I'm just calling them high and low, but really they're in the code, they're going to be C and D. Well, the problem now is you can't really implement this algorithm exactly, because if you look at this, right, what you're going to be doing is you're going to be starting with the number 0. You're going to add this to this D register. Okay, that's fine. But the next iteration, you're shifting this over, and you're going to have to add across 2 different registers, which doesn't really make any sense. So you can't really do this algorithm exactly how it's written. So you're going to do it in a slightly different way. What you're going to do is it's going to be a pretty simple process that's going to just require a few very simple steps. And another thing to point out is, so for doing this multiplication, you have to multiply a single bit by this top number. That's sort of, I mean, the whole point here is to implement multiplication. And if we have to do multiplication in order to do multiplication, that sort of defeats the purpose. But if we look here, this is going to be very, very simple, because we're either going to be multiplying by 0 or by 1. Right? We don't actually have to do that multiplication. We know that if this bit is 0 here, well, we're just going to be adding 0. And if this bit is a 1, we're just going to be adding this number. Right? We don't actually have to do any sort of multiplication. We can just do if statements here to actually perform that multiplication, which is really, really nice. Okay, so the way that we're going to do this is, let's say we're doing this times this again. Actually, I'm going to choose slightly different numbers. I'll do that right here. So 6 times 3. So the first thing we're going to do is we need to keep track of what bit we're on. So we're starting with this bit here. Now what we're going to do is we're going to inspect what it is. And I guess I'll write this over here. So we have our C register, which is going to be our high register. I'll just write high actually. So we have our high register and we have our low register, which are each going to just be 4 bits. So the first step is we look at this bit. We see that it's a 0. So that means what we're going to do, and actually we'll start off with both of these just as 0. So what we're going to do is we see that this is a 0, and so we don't have to do anything, right? We don't have to add anything to this high bit, to this high register, because it's a 0, right? We don't want to add this onto the high register. And notice that normally we would have added to the low, but this time we're going to add to the high, and we're going to do only addition to the high, and then use shifting to shift things over into the low. So we see that this is 0, so we're not going to add anything to high. The next thing that we do is we're going to shift every single bit over by 1 to the right. So this 0 is going to come over here, this 0 is going to come over here, here, and then we're going to take this 0 and we're going to shift it into the high bit of this one, and then keep going. Now, in VML, there is no direct way to do this. You're going to have to essentially find a way to hack it. It is possible. You have to do a couple of instructions to do it. Then you'll want to think through that, but it's not too difficult. And then as this top bit here, we're just going to put in a 0. Okay, so here we didn't really do anything, but that's fine. So now we move on to the next bit. So now we move on to here. We see it's a 1, so what we're going to do is we're going to add this top number here to high. So this will become 0, 0, 1, 1, and low is just going to stay the same. And then we shift. So we'll shift everything to the side. So now we end up with, we'll shift in a 0, then this 0 goes here, 0 goes here, this 1 will come here. This 1, again, goes over to the other side. And you'll, again, need to figure out a way to do that. And then, again, all the rest of the zeros just get shifted over. Then we move on to the next bit. So, again, this is, we added 0 here. Here we added, because this was a 1, we added the top number. Then we shifted it over. So now we're on the green. It's a 1, so we'll add the top number. So we're doing that addition right here. So we're adding 1, 1 to this. Well, this is 3 and this is 1, so our result is going to be 4 here. This would just be done using an add operation or something. And so we end up with this. Our low is going to stay the same. And then we shift everything over. So here, again, this 0 is going to shift over, 1 is going to shift over, 0 shift over. This 0 is going to come over here, 1 is going to shift over, everything's shifting over, and the 0 is just going to appear up here. And then finally, we see that the top bit is 0, so we're going to add 0 to it, and then we have to shift still. We still have to shift. So it does not matter, like if we're looking at a 32-bit number, it doesn't matter if that 32-bit number has 31 ones here, or 31 zeros here, and then a 1. You have to do the shift operation 32 times every single time. And in VML, registers are 32 bits. So you're going to have to do the shift part 32 times. It does not matter if you run out of bits. If the rest of the bits are all 0, it does not matter. You still have to shift. Because the problem is we're computing everything in the high, and then we're shifting it over. And so if we were doing here, we would just compute in the low and then shift what we're adding over and over and over and over. But what we're doing instead is we're starting in the high and then shifting that over and over and over. So we have to shift exactly 4 times if we're doing 4 bits, or exactly 32 times if we're doing 32 bits. So here, although we didn't add anything, we are going to go ahead and shift. So 0, 0, 0, 1, this 0 gets shifted over, this 0 is shifted over, this 1 shifted over, and the 0. And so here we have 6 times 3, that's 18. And this number right here, if we rate it as one 8-bit number, well, this is 16. Yeah, and this is 2. So this is 18, right? Really, it'll be stored as 1 and 2 in 2 different registers, but you want to read that as one single binary number. And that's pretty much it. You just, if this single bit here is a 0, you're not going to add anything. Otherwise, and then you do a shift. If the bit is a 1, you'll go ahead and add the top number to the high and then shift everything over. And this is the algorithm you have to implement. You cannot implement another type of algorithm because you want to end up with these high bits and these low bits. Otherwise, it's not going to work. Modern day computers have multipliers in them, hardware multipliers, that more or less do exactly this. They're usually a bit more sophisticated, but they're essentially doing some variation of this algorithm in parallel. But you can think back to the times when a computer only had an adder and you wanted to multiply things together. You had to have an algorithm for it. So this is a pretty decent algorithm, at least for it's relatively simple. So one last thing is you need to be able to check individual bits. How do you do that? Well, let's say I have, and again, I can't stress this enough. VML is in 32 bits, and you need to do everything for 32 bits. I'm just showing 4 bits because I don't want to draw 32 bits. So let's say we have this number here. How can we check to see what this bit is here? Well, if we use bitwise AND with this number here, well, okay, let me just replace these with variables. So let's say I don't know what these bits are. There's just A, B, C, and D, right? And if you just have a number in a register, you don't actually know what value that register has. The register just holds a value, and then you want to just do an operation on it. It's the same thing like in a programming language. If you have a variable x that's an integer, it just holds a number. You don't necessarily know what it is. You can check to see what it is. Right? You can say, is x equal to 3? Or is x equal to 4? Is x greater than 5? Right? You can do those checks, but you don't know what it is. So let's say we have this. Well, if we do this bitwise AND here, well, 0 and anything is just going to be 0. So this bit's going to be 0, this bit's going to be 0, this bit's going to be 0. But 1 and anything is just the anything. So if we do bitwise AND with this thing right here, which is known as a mask, it's essentially wherever it zeros, it covers up what the actual values are. But whatever it's a 1, it's sort of like a hole, and it lets that value through. So it's sort of like putting on a mask on that number. And then you can isolate this bit. And then, well, either this is going to be this number or it's going to be this number. So if the result is 0, then you know that there must have been a 0 in that position. If the result is 1, or if the result is anything else, you know there must have been a 1 in that position. Because I mean, if I do bitwise AND, let's say here, let's say I want to know what this bit is. Well, what I can do is I can do this bitwise AND with this number here. Well, everywhere it's 0, the result's going to be 0. But wherever it was a 1, it's just going to keep that value. And now this number is either 0 or, I guess, 4 here in this case. So really what you want to just do is check to see if it's 0. If it's 0, do something. Otherwise, you know that bit must have been a 1. And you can check to see what individual bits are. And, I mean, you're going to be checking the bits in this order. So, I mean, you're going to be starting off, let's say, with this number. Again, using 4 bits as an example. So you start here, and then you can just shift this number to the left, and then you end up with this, and then shift it to the left, and you can end up checking each individual bit like that. The multiplication algorithm document explains this in a little bit more detail, so you can definitely take a look at that. But yeah, this is sort of high level the multiplication algorithm.